My name is Marco Huber from Fraunhofer IGD in Darmstadt, Germany, and I will present our work studying comparison score uncertainty and verification decision confidence towards transparent face recognition. When human operators are asked if two images show the same individual, they can intuitively state how sure they are about the decision. The estimation of confidence and uncertainty regarding decision making is important and common for humans. However, current state-of-the-art face recognition systems do not offer such a confidence or uncertainty estimate. Providing such an estimate would increase the transparency of face recognition systems, which is important as they are used in critical systems such as security, law enforcement, and access control. In this work, we follow the definition of Peterson and Pitts from psychology and differentiate between uncertainty and confidence. Uncertainty refers to the belief about the variability of possible outcomes, and confidence refers to the belief that a given prediction is correct. Both terms are therefore not interchangeable. For face verification, we can therefore only determine a confidence for the verification decision and an uncertainty estimate for the comparison score. An example is shown below in the image. In our work, we propose two main contributions. First, the score uncertainty that allows the interpretation of the propagated uncertainty of the comparison score, and second, the decision confidence that allows the interpretation of the reliability of the decision. As both of our contributions build on model uncertainties on feature level, we first introduce how we estimate the embedding uncertainty. Given a face image I and a face recognition model M, we estimate the feature uncertainty in each feature dimension by using dropout as a Bayesian approximation of the model uncertainty. We create a stochastic set of feature representations based on different dropout patterns applied and calculate the uncertainty in each dimension as a standard deviation of the set. To decide whether two embeddings x and y represent the same identity or not, we need a decision measure. Typically, the cosine similarity is used to determine the similarity of two vectors that represent two face images. Since the face embeddings are often normalized before the comparison, the cosine similarity formula simplifies this formula shown below. To obtain the uncertainty delta SC of the comparison score SC, we now make use of the propagation of the uncertainty formula while neglecting cross-feature correlations and assuming independence of the dimensions. Applying the propagation of uncertainty on this cosine similarity leads to a formula to calculate the score uncertainty delta SC. Delta SC therefore estimates the uncertainty of the comparison score SC based on the individual uncertainties of the features of both embeddings for the comparison x and y. This estimation allows a deeper insight into the calculated similarity, as it additionally takes the uncertainty of the representation into account. Since the score uncertainty delta SC only indicates how certain the model is about the score and not how confident it is about the decision made, we also propose the decision confidence approach. Following the definition of confidence, which refers to a decision and the belief that the decision made is correct, we incorporate the decision threshold D into our approach. As we need a derivable function to propagate the uncertainties to the decision, we estimate the decision step function by a modified sigmoid function that incorporates the decision threshold D and a scaling factor alpha. The alpha value weights the trade-off between the importance of the uncertainty and the distance to the decision threshold for the confidence. To define our confidence estimate, we apply the propagation of uncertainty formula again and subtract this uncertainty from 1 to get the intuitive understanding from increasing and decreasing confidence in a natural sense. To show the validity of our proposed uncertainty scores and decision confidence, we use three different well-performing face recognition models as a basis: ArcFace, MagFace, and CurriculaFace. All models share the same ResNet-100 architecture and have been trained with a specific loss function on the MS1 version 2 dataset. We use these models to show that our proposed uncertainties and confidence are model independent and can be transferred to a range of diverse models. For the evaluation, we utilize two diverse and difficult datasets with a high variance in quality, ADIANS and cross-quality LFW. We evaluate both score uncertainty and decision confidence using error versus reject curves. They show the verification error rate over the fractions of unconsidered face images based on some measure. In our case, we first remove either the pairs with the highest uncertainty in the score or the pairs with the lowest confidence in the decision. The error should therefore decrease if the most uncertain or the least confidence pairs are not considered. In the score uncertainty evaluation, we compare our approach with the MagFace face image quality values that estimates the utility of a single image to be used for recognition purpose. For each pair, we treat the minimum quality of both images as the uncertainty of the comparison. In the confidence evaluation, we compare our approach with intuitive confidence. This intuitive confidence is derived from the comparison score and it's to the decision threshold. The intuitive idea is that the confidence of correct decisions increases with higher or lower similarity starting from the decision threshold. The formula for the intuitive confidence is also shown on the slide. And for all experiments, we keep the threshold fixed. We compare our proposed score uncertainty, delta SC, with the face image quality values provided by the MugFace embeddings. We can observe that the performance improves as fewer errors are made when those comparisons are removed where the score has the highest uncertainty. This can be observed on all three face recognition models on both datasets. The steadily decrease indicates the strong usefulness of the estimated uncertainties. Even if the minimum quality is in some cases better than our proposed uncertainty, we emphasize the difference. The minimum quality reduces the problem of inaccuracy of the comparison to the quality of the image, while our approach considers both images and their mapping. For the evaluation of the decision confidence, we also investigate the performance by looking at the error with reject curves and compare our proposed decision confidence with the intuitive decision confidence. It is important to note that both confidences are threshold dependent, as it defines the confidence about a made decision. On the aliens dataset, we can observe that a minor improvement can be achieved by using the proposed decision confidence in comparison to the intuitive confidence. A larger improvement can be observed on the cross-quality LFW dataset. Overall, the proposed decision confidence estimates the reliability of the decision more accurate than the intuitive confidence. In these heat maps, we compare the distribution of the confidences depending on the score on the aliens dataset using the MugFace model. The black asymptote indicates the decision threshold, while for the intuitive solution, the same comparison score leads to the same degree of confidence. In our proposed approach, the uncertainty is also taken into consideration. This allows a more natural interpretation of confidence, as it is not only depending on the similarity, but also on the uncertainty of the similarity of the considered pair. In our work, we propose two things. First, we propose to estimate the uncertainty of the comparison score of face recognition models using model uncertainties and the formula of propagation of uncertainties. And second, we propose to provide a decision confidence on the decision of face recognition systems by utilizing the model uncertainties and the decision threshold. In our experiments, we showed the validity of our proposed uncertainty and confidence estimates. By outperforming the intuitive decision confidence, we showed that more sophisticated ways of interpreting the confidence of decisions are possible and useful and may provide deeper insights into the used models. We introduced the new concepts of score uncertainty and decision confidence to highlight the need for transparency and reliability in the biometric decision-making process to increase the trust and reliability of face recognition systems. With this, thank you very much for your attention. If you have any questions, feel free to reach out to me. And yeah, thank you very much.